Yeah, so the previous class we just had a quick look at this expression for number density of electrons in an interval from E1 to E2. So what is this expression? So I have two energy levels E1 and E2 and I want to find out how many electrons are there totally between E1 and E2. So the expression for that would be integration from E1 to E2 g of E f of E dE, where g of E is the total number of energy levels that exist between E1 and E2. Why the number of energy levels? Because energy states are not continuous, they are quantized, right? So energy can take only certain specific values. So between E1 and E2, how many valid possible values of energy are there? That is given by g of E. Then f of E is the probability of finding an electron on each of these levels, the probability of occupation of an energy level by electrons. So this is the expression, and the expansion for f of E we did not derive, but it was given to us as an expression 1 by 1 plus e raised to e minus ef by kt, if I'm not wrong, and we looked at that expression and we looked at something called the Fermi energy level and all that in the previous class. So f of E we are somewhat familiar with it now. So in this lecture we are going to be trying to derive g of E, which is the number of allowed energy levels between E1 and E2. So before we start the derivation, this expression for energy is something we derived, I think, when we were doing potential well, if I'm not wrong. So we got this expression, energy equals n squared h squared by 8 ml squared, where h is Planck's constant, m is the mass of the electron, L is the length of the potential well or cubical box, whatever you call it, and n represents the level of excitation, as in n equals 1 is your ground state, and then n equals 2 is your first excited state, n equals 3 is your second excited state, and so on and so forth. So n can take positive integer values starting from 1. So when we did a 3-dimensional potential well or cubical box, we split this n further into nx, ny and nz, which represent the quantum numbers in the 3 directions along the x-axis, y-axis and z-axis. So we looked at this concept called degenerate states, where the total energy is the same but the actual quantum numbers are different. For example, you take 121, 211 and 112. The overall value of energy will be the same because nx squared plus ny squared plus nz squared will be 1 squared plus 2 squared plus 1 squared, which is 6. But the actual nx, ny, nz values will be different. 121 is different from 211, is different from 112. So the orientation along different axes, that will be different, but the total energy will be the same. So that is called degenerate states. We saw that one concept, and why I am talking about all this is we saw this idea of quantum numbers along 3 different directions, nx, ny, nz. So that is what we are going to take and look at in detail in this section, and that knowledge, that idea of 3 dimensions is going to help us understand more about this g of E function. So what is our objective today? We want to derive an expression for g of E, where g of E is the number of allowed energy states between any 2 levels.